Okay, so on page 294 in your Finney text, we're talking about fundamental theorem again. So we did this in Calc 30 a while ago. We're going to revisit this with some different style questions. So some questions that we really haven't looked at much before. It would be, I think, helpful for us to review what the fundamental theorem says. There's a few important things that it says. This is very, very important, and I will kind of break this down kind of as we go. But I think I'd like to read what it says in your textbook about the fundamental theorem of calculus. The fundamental theorem of calculus is what it is referring to. The fundamental theorem says that every continuous function f is a derivative of some other function. Okay, so every function is a derivative of another function. So if you take the integral of some function f of t in this case, you take the integral of it, and then you take the derivative of that integral, you get the function back. So every function is a derivative of some other function. Okay, so it's the result of, so you can differentiate to get this said function. Namely, and this is the what we're going to talk about more today, the integral of f of t. And notice that there's an x there in the limits of integration. So we're going to talk about that today. It also says that every continuous function has an antiderivative. The fundamental theorem also says that the process of integration and differentiation are inverses of each other. So that's why, check this out, you take the derivative of an integral and you get the function back. Now you notice how this is t and this limit here is x and this is x. That's going to be the little difference today, and we're going to do some questions that look a little bit different. So if any equation deserves to be called the fundamental theorem of calculus, this one surely is. So it relates the derivative and the antiderivative, or the integral and the derivative. Okay? So if you have a function, you can take the derivative of that function and get the derivative. If you start with the derivative down here, you can integrate or take the antiderivative to get this function. You can anti-differentiate again to get the integral. So we have integral, function, derivative. Going down this ladder is differentiating. Going up this ladder is integrating. Okay? So every function is a derivative of another function up here. It's integral. Okay? And every integral has a derivative. If it's continuous and differentiable and all that sort of stuff on the interval, right? We learned about that. Okay. So let's unpack this a little bit more. I'm going to zoom into this. Just, I don't know if you guys can see that all the way to the back there. But anyway, so what this is saying is that if we take the derivative of an integral, we get the function inside back. So these kind of take care of themselves. They kind of balance each other out, right? Or counteract each other. That's fine. The weird part is this f of t dt, and then we have d over dx with the limit of x. And then we have this a in here for some reason. Like, what is that all about? So that's kind of what I want to talk to you about today. This a is a constant, and this constant is on the interval, the closed interval, a to whatever, to b. So this is somewhere on here. It can be a, can be all the way up to b. It's somewhere on this interval where the function is continuous and differentiable. Okay, so it's just any constant. This is the kind of cool part here. Okay, if we have x as an upper limit or as an upper boundary of the integral, what this is sort of saying, okay, let's say this is a right here, and here is our f of t. Okay, so this is f of t. Okay, here's t. Let's say it's time. It's some function, some happening over time, right? So if I go to a to some x value, this becomes f of x, doesn't it? That little point becomes f of x. Okay, so let's back up and let's say that the upper limit is x. Well then, if this is the point f of x, and if we move this x around, every point on this could be f of x. Right? And if we're talking about integral, I'm talking about, another way to view that is the area, okay, underneath the graph between a and x. And this area is represented by the integral of f of x if I'm going to x. I know it kind of seems like it's bumbling all around there, but if we have x as an upper limit here and we're differentiating the integral, it's basically the same as we're talking about f of x instead of f of t. So this x basically gets put right in there, especially because we're differentiating with respect to x. So this x gets put in there, and this also becomes an x. It's kind of like this d of x now turns to a d of x, this dt turns to a d of x, and they can kind of cancel out, and then we take the derivative, and the integral's gone, and we just left with f of x again. Okay? So I don't know if that's the best way to explain that, but the bottom line is if you have an x as an upper limit of integration here, then, and you take the derivative of that, you just get f of x out, whatever is in here with the x in it. Okay? Now that translates into, let's do this question below, or let's take a look at anyways, the example 1. It's actually pretty simple and straightforward. The only tricky part, okay, is maybe the constant on the bottom, okay? Because this constant is almost something you can just ignore, all right? It's almost like you ignore it. It's assumed that this constant, remember pi is not a variable, it's a constant, 0 is a constant, it's a number. So it's assumed that this number is on the interval somewhere, okay, where cos of t is defined. And that's true. I mean, you could do cos of pi, right? Cos of negative pi, that's defined. So that's on the interval. But when we're talking about just the general sort of, this is a derivative, right? So what does the derivative look like? Well, it looks like the function that's inside the integral. So it's almost like an indefinite thing. So if we're talking about a definite integral, then this would come into play and the upper limit would come into play, and we would have a definite number answer. But if we don't have a number, we have just a variable up here, then we can interpret this, and here's the solution down here, okay? We can interpret this as, how do I find out what the derivative of this integral is? Well, if this is x, I simply put it into the function in there, and it becomes cos of x. And I can use that to find the definite integral from this, constant value to whatever another constant value we may put into it. Okay? So it would the bottom line is that this x, if it's an x here, it just goes in for the variable, and it does not matter what this is. So this is 0, doesn't matter. If this is x, and we're actually differentiating with respect to x, then I can go ahead and put x in for the variable and just call it a day. And that's what it is. So you're taking the derivative of the integral, you should get the function back. And if that function has an upper limit of x, the function is expressed in terms of x. Okay? Now you may have questions, but let's do, it's pretty simple. Let's do one together here, and then if you have questions about the process, let me know. Okay? I'm not really here to explain for an hour why this is. I'm just trying to help you recognize a question and do it with sort of just a real basic slight explanation. So this one here, okay, if we are finding the derivative, so find dy of dx of this particular thing right here, okay, there's y, then what I want to look at is I want to look at, okay, if this is a t and this is a dt, but I want to find dy over dx, as long as I have x up here, I can simply plug in x in for there. So the derivative of the integral just gives us this function back, and it's going to be x cubed minus x all to the power of the fifth. So we just put that in there. And that's literally what it is. So the derivative undoes the integral, and we just slide x in there. Okay? So what do you think 5 would be if we're finding the derivative here? Doesn't matter what this 2 is, as long as this is an x, we know what to do. Okay? So we put that x in there, and that should be tan cubed of x. Okay, so if we look at example 2 on page 296 in your Finney text there, what we see is we have something different, because this would be the next step, the next level. I'm finding dy dx, and I have an integral. Oh, great. I'm finding the derivative of an integral. This should be easy. And it is pretty easy, except for the fact that this is not an x. Again, constant, who cares? Doesn't matter. This is not an x, this is an x squared. So if we're taking the derivative of something and this inner function, right, if this goes inside there, we have to account for the chain rule, basically, right? So if you put x squared in there and you just expect to get cos of x squared, then you kind of are forgetting about the chain rule part of taking a derivative. And so there's one little thing that we have to do if we have something that's not just x in there. Now, the way they explain it in the book here, okay, and you'll see this u substitution with the integral. And I think we have done this before. Yeah. Again, this is the way the book does it, so this is the way I'm going to show you. There's a lot of things that are good in here. You may be able to skip this step, okay, this one step right here, eventually. But let's just say that this is a function that is not just x, so the derivative of which is not just 1. That's important. If it's anything other than just x, then we have to consider this as a function in which we must take the derivative of. So it's the chain rule has to apply. So what they do is they say, okay, this is not just x, make this a u, and write what u equals on the side. If we're taking the derivative of both sides, then what we need to do first then is to take the derivative of this function y with respect to u. So we talked briefly about Leibniz notation in Calc 30 before. This is where Leibniz notation, when it comes to the chain rule, this is where it's really helpful. And so dy with respect to u looks a certain way, but we don't want dy du. We want dy dx. So that's when we have to multiply by the derivative of u with respect to x. So that's where we take the derivative of u over here, so du, right? Derivative of u with respect to x, dx is going to be 2x. So that's got to come into play. So if we take the derivative of the integral of cos, that just becomes cos. Because this is now a u, we're going to put that as cos u. But we have to do the chain rule. And so cos of u becomes cos of x squared. But because we're differentiating and this is not just an x, we have to multiply by its derivative, where we get this. Okay? So again, if you have this, what was it, 1, 2x squared, cos t dt, okay? So if you said, listen, I understand that this is not just an x. If I take the derivative of this with respect to x, I'm going to have to go cos of x squared, and then I'm going to have to multiply using the chain rule by 2x. So you can kind of see how you can kind of bypass this u substitution for these simple ones. Okay? You can kind of bypass that a little bit. But this is the explanation as to why it works. And sometimes they go over the top a little bit in explaining why this works in order for you to understand why you do it. So what I'm saying is that, hey, if you have something like this, treat this as a u, which means that you can just substitute it in, but you've got to multiply by its derivative as well before you're totally done. Okay? Okay, so that's the one slight little difference there. Just make sure you remember the chain rule when you differentiate. Okay, so why don't you guys try 9 and 10. I guess this would be 10 from your assignment. So take a minute. Try 9 and 10 with this sort of second level type. Okay, so if we take the derivative of both sides here with respect to x, you can put this in for the variable, okay, understanding that this really is u. So you could go in there, multiply it by du as well. And so this becomes the derivative with respect to x, of 0 to x squared of e to the t squared dt becomes, this kind of cancels off with the integral part, and you have e to the x squared squared times the derivative of this here, which is 2x. So this becomes 2x e to the x to the 4. Did you get that for an answer for 9? Or anyone not see why they didn't get that? You guys are good? Okay. Okay, so again, it doesn't matter if this is t or u or w or k, it doesn't matter. This is what has to go in for u here. So I don't know if they're just trying to mess you up a little bit, but this goes in here. Because this is not x, we do need to, again, at the end, multiply by d, the derivative with respect to x of 5x, right? So let's do that. The derivative and the integral cancel each other out. We put in 1 plus, and we'll put in 5x all squared over 5x, and we'll make sure we multiply by the derivative of 5x, which is 5. So the 5's cancel out, and you should be left with 1 plus 25x squared all over x. I think that's what you should end up with there. If that seems, did anyone else get that? You guys get that? Yeah? Okay. All right. I guess there would be one more here, and I'll talk about this one as well. Okay, just going to zoom in. Won't move that. I'll just zoom in on it a bit. So ignore the black part there. I clipped it out of a digital copy that had the answer in there, and I couldn't really cover it up very neatly, so just don't want to spoil the surprise for you. So anyway, so what happens if you have a constant on top and the variable on the bottom? This is the difference. Well, maybe you can remember what's the similarities, or what's the difference between if we have a, b as limits of integration, okay, of f(x) dx, versus, right, this one, the limit of b to a of f of x dx. It's the negative of it, right? They are negatives of each other. Awesome. So if you kind of go one way, it's positive. If a is less than b, okay, if you go the other way, it's negative. So the other thing is, what that means is you could flip them around and then just add a negative and do everything the same way that you did before. So that's what we're going to utilize here, okay? That's what we're going to do here. So if we're going to flip around, put a constant on the bottom and the x on top, we just got to make sure we put a negative on the outside, okay? So this is easy now. We have a constant. We'll assume that it's on the interval where this is defined. It's positive. This is a square root. So this is positive, so it's probably okay. If it was negative, we might have a problem. Right? Maybe, right? We don't want a negative under a square root, but this is positive, so that makes this positive. Everything's good. So then we just go negative of the square root of 2 times x to the 4th plus x plus 1. And my pen is super thick because I'm zoomed in, of course. But it's just this, negative 2x to the 4th plus x plus 1. And I think that should be your answer there. Okay. All right, so let's get back to regular size view there. Okay. Any questions? Okay, just, I guess, remember chain rule. When you're differentiating, just remember chain rule. That's the bottom line. Okay, so I think that I would like you to do number 1, 2, You could probably do number 1, 2, especially because I added this other one. 1, 2, let's go 16. 1 to 16 on page 302. So exercises 1 to 16, page 302. Okay. You don't have to worry about that. I don't think.